Hey everyone, welcome back to another video of CIE A Level Physics revision playlist. Today we're going to talk about the errors and uncertainties, which is a subtopic of the same topic, physical quantities and units. Now, first off, we need to discuss what is the difference between a reading and measurement. For some of you, the difference might be very obvious, but the difference between reading is that the reading is just a single determination of that value, is a single determination of the value of an unknown quantity during an experiment. In short, this is a single observation. But measurement is the result of a series of readings. So measurement is a result of analysis of multiple readings. Now, this was just an overview of what's the difference between a reading and a measurement. Now, what are errors and uncertainties? So, errors are basically deviations or mistakes that cause in the experimental process that lead to a difference between the measured value and the true value of a quantity. Now, even if you had just written this thing, a difference between the measured and the true value of the quantity, even that would be correct also. But what are uncertainties? Uncertainties are basically the range, the estimate of the range within which the true value is expected to lie That's it. Right. Now, the types of errors. There are different types of errors leading to uncertainties. The first one is easy, systematic. Systematic errors are repeatable, consistent errors. So they are consistent, repeatable errors resulting in a bias in one direction. That means either it will cause a measurement higher than the true value or the lower than the true value. Now, how are they caused? Probable causes. It could be due to flaws in experimental setup, calibration errors, method. For example, zero error is a type of a systematic error. Another type of error that you know, reaction time. Reaction time is a systematic error. These are two common examples of systematic errors that we know. Now, how are they reduced? So, systematic errors, they need to be eliminated. They can be eliminated once you identify. So, systematic errors can be eliminated once identified and corrected. Whatever the cause is, maybe it's a zero error, maybe it's a reaction time, or there is a faulty instrument or something. Faulty instrument also. Whatever the case is, once you identify that cause and correct it, your systematic error will go. One thing you need to remember, it cannot be reduced by averaging. That's not how this works. However, the other one, which is random errors, that can be reduced by averaging. Now, what are random errors? So these are unpredictable fluctuations causing in the measurement process, causing measurements to be scattered around the true value. That means it can be above and below the true value. Now, possible causes. They couldn't any unpredictable errors, for example, it could be parallax error. Parallax error is random because your eye angle can change. Changes in temperature and pressure. Sometimes they can affect certain measurements. Now, how do we reduce them? They can be reduced. They cannot be eliminated. They can be reduced, however. They can be reduced by taking multiple measurements and averaging them. Why? Because when we say scattered around the mean, these values, they are, for example, if this is the true value, for example, the readings would be scattered somewhat like this around the mean. So if you are familiar with statistics and the Gaussian, the normal curve, you would know that there's a very higher chance or probability of a value being near to the mean. So they can be reduced, not eliminated. So point being reduced, not eliminated. Not eliminated completely. Now, another concept that is related to both of them are precision and accuracy. Now, let's see what are these and how the systematic and random error are playing a part in this. So, precision, accuracy. Now, precision, we know what precision means. It's a quality of readings to be close to each other. So, a measure of how closely the individual measurements agree with each other. Sorry, each other. In short, how close they are to each other. So basically, how close they are to each other. Now, accuracy, on the other hand, measures how the measured value or even the average of multiple measurements agrees with the true value. So, a measure of difference between measured value and the true value. Lower the difference, higher the accuracy. Lower the difference, higher the accuracy. Now, what factors affect accuracy and what factors affect precision? I think we already know that. Now, precision is associated with random errors, and accuracy is associated with systematic errors. How? Let's see the difference between a few pictures. We just drew the Gaussian curve or the normal curve, which we are already familiar with. So let's see if this is the true value. Let's uh, draw that a few more times. Over here, over here, over here. All right. And this is the true value, true value, true value, true value. Now, if we have a curve like this versus a curve like this, oh, sorry, no. Actually, wait a second, we can skip this thing for a bit. These two, see, there's a lot of spread. The mean would be over here. Mean value would be somewhere over here, but the spread is very large. So large spread means low precision. Low precision. At this point, we don't know where the actual value is. Similarly, if we look at this over here, this is the mean value, or this. There's a small spread, small standard deviation or variance, you could say. It would be high precision. That means the values are close together. We said that over here. But accuracy, on the other hand, means two things. If, for example, you are getting like this and you are getting somewhat like this. So if you notice, here lies the mean of this value and here lies the mean of this data. So this is inaccurate because there is a difference between the true value and the mean of the measurements. And this is what systematic error usually means, that it causes a consistent bias between the readings. And this would be accurate. And if, for example, we do one change over here, if we make this more thinner spread, it would be accurate and precise. The more thin the spread is, the more precise it would be. The more closer the mean is to the true value, it would be more accurate. All right, this was just a brief thing. Now, how do we express uncertainties? There are majorly two ways, but we can extend them to three ways. There is an absolute uncertainty. There is fractional uncertainty, and this can be extended into a percentage uncertainty. functionally they would both be the same. They represent the same thing. Now, absolute uncertainty. So for example, if I have a quantity x plus minus sigma x, this would be the absolute value, or absolute uncertainty, sorry, this is delta, my bad, I misspoke. This is small delta. It means change or a small deviation. So this thing is our absolute uncertainty. For example, 5.0 plus minus, let's say 0.1 centimeter. Let's say this is, for example, 5.2. 0.1 would be the absolute uncertainty. Similarly, in fractional thing, we can express it the same way using the same variables that we have introduced. This would be fractional, and if you times this by 100, this would be percentage. So if we express the same number this way, this would be 0.1 over 5.2, and this would be 0.1 5.2 times by 100%. Notice that what we did over here, the decimal places that we have written for the absolute uncertainty agrees with the value, the mean value, mean value over here. So this is something that you need to be very careful about. So the point to note over here about the decimal places and significant figures to remember over here is that the uncertainty, the absolute uncertainty, usually can be reported with one or two significant figures. In AS, we would stick to one. Any question you see, we need to use just one significant figure, and that means adjusting the mean value or the raw value for that also. So, for example, what that means is the raw measurement you have for example, raw measurement is 12.34, let's say 5 centimeter, but the uncertainty, absolute x, or the delta x, is plus minus 0.2 centimeter. You know this from, for example, the instrument itself. So how will we write the final measurement? See, one significant figure, one decimal place, we would round it to 12.3. 12.3 plus minus 0.2 centimeter. So final measurement or reported measurement has same decimal place, same number of decimal places in the value, mean value, or whatever this value is, measured value, and uncertainty. So that's how we decide that. For fractional or percentage, Again, you can have one or two significant figures as you find appropriate. But the rules would be the same. Now, the propagation or the compounding of these uncertainties when you're adding, subtracting, or multiplying, dividing quantities, that is what's going to change the game over here. So, uh, propagation, compounding, uncertainties. Now, it depends on whether you are taking a sum or a difference, or you are taking a product or a quotient. So for a sum or a difference, remember you need to add absolute uncertainties. Even if you are subtracting the two quantities. And again, the number of significant figures and uncertainties, remember, it will have the result will have same number of decimal places as the input with the fewest decimal places. And then you will have to adjust the absolute uncertainty also. Similarly, for product, quotient, you have to add fractional or percentage uncertainties. But if you notice both of these, they are giving us two different things. One is giving us final absolute uncertainty. The other one is giving us final fractional or percentage uncertainty. It's not giving us the absolute uncertainty directly. So we have to find that carefully. And for this one, it's the significant figures that we have to use. So the result has the same number of significant figures as input with fewest significant figures. And uncertainty, you have to adjust the decimal places and significant figures of the uncertainties. So you have to manage that also, right? Okay, so for example, let's take a few examples before we see some past paper questions. Actually, we can see the past paper questions also. Oh, wait, sorry, I forgot one thing. What if you have a power exponent? You will add or multiply that power with the percentage power or exponent with fractional or percentage uncertainty. Now, let's take an example before we see. Let's say you have two lengths. L1 is 4.5 plus minus 0.5 centimeter, and L2 is 5.9 plus minus 0.1 centimeter. Let's take the sum and the difference. So for L1 plus L2, what we would do, we need the sum for that also. So L1 plus L2, that would be 4.5 plus 5.9. But we would also need to add their absolute uncertainties. That would be 0.5 plus 0.1. So this one, 4.5 plus 6 would be 10.5 and then 10.4. And this one would be 0.6. So final value would be 10.4 plus minus 0.6 centimeter. And notice over here, one significant figure, one decimal place that agrees with this uncertainty. But what if we were subtracting these two quantities? What if you were doing L2 minus L1? So we would do L2 minus L1. That would be 5.9 minus 4.5. But for the absolute uncertainty, we would add these two the same way. So this would end up being 1.4, and this one would remain 0.6. So final value would be 1.4 plus minus 0.6 centimeter. Now let's see the multiplication route, for example. Let's say you have two lengths. Length is, let's take an area case over here. You have dimensions of a square, rectangle. We'll come back to the square. So dimensions of rectangle. L1 has, let's say, 5.0 centimeter, and L2 has 3.5 centimeter. Both of them have the same absolute uncertainty. Let's call it 0.2 centimeter. So we need to find out the area. So area, length times by other length, so 5 times by 3.5. So 5 times by 3.5, that would be 17.5. Oh, sorry, centimeters squared. But what about this thing? Oh, sorry, what about the area? Delta area. But we can't find it that way because we have to find it using the fractional or the percentage way. So there are two ways to handle this. Either you find out the percentage uncertainties of both lengths first, or you add the fractional uncertainties. So 0.2 over 5 plus 0.2 over 3.5. So let's find the value. So 0.2 divided by 5 plus 0.2 divided by 3.5. You see, you get 0.097, 0.097, which is roughly 9.7%. This is still not the absolute. To find out the absolute uncertainty in the area, what you need to do is you need to cross multiply. Sorry, this was the value, my bad. Value of area with this. So value of area was 17.5 times by 9.7%, or instead of 9.7%, you can use the 0.097 also. So this value times by, oh, sorry. So answer, no, sorry. 9.7% times by 17.5, you get 1.6975, which you can round it to 1.7 centimeter squared. Or for one significant figure, 2 centimeters squared would be fine also. So final value could be reported as 17.5 plus minus 2.0 centimeters squared. If you could, however, make it 18 plus minus 2 also, but both of these would be fine, because if you're in AS, we have to use one significant rule for the uncertainty, so that would be fine this way also. That wouldn't be necessarily breaking any rules. Right, okay. Now let's see some past paper questions to better practice this. All right, so let's see this. A thermometer can be read to an accuracy of plus minus 0.5 degrees Celsius. This thermometer is used to measure a temperature rise from 40 degrees to 100 degrees Celsius. What is the percentage uncertainty in the measurement of the temperature rise? So first off, we need to find out the temperature rise, the change in temperature. That is 100 minus 40, which is 60 degrees Celsius. But actually, we can just call it T just for simplicity. And the delta T, or like this delta T, either way, whichever way you want to write, this would be 0.5 plus 0.5, which is plus minus 1 degree Celsius. So T plus minus delta T would be 60 degrees Celsius plus minus 1 degree Celsius, or 60 plus 1 degree Celsius this way. I don't know why this is not working. Right, okay. Right, degree Celsius. Now, if we want to find out the percentage, we would do 1 over 60 times by 100. So 100 divided by 60 would be 1.66, or 1.7 to two significant figures. The value of quantity X has a percentage uncertainty of 2%. The value of quantity Y has a percentage uncertainty 4%. Value of quantity W is calculated from the values of X and Y. The value of W has a percentage uncertainty of 8%. What could be the relationship between X and Y? Now notice that when we multiply or divide, we add, in this case, percentage uncertainties. So 2 plus 4, that's not equal to 8. That means there is something going on. What could possibly happen is that this X could be happening this way. Could be one possible way of doing this would be this way. That means X would be squared and Y would come out this way. Similarly, since the same would happen in division, We could have x squared over y also, or y over x squared also. So neither of these would have any effect. So x would be squared, actually, sorry. So x would be squared. If you do 4 times by 2, if the y was squared, you would have 4 times by 2. So 8 would be 8 would be reached without the involvement of x. So 2 times by 2 plus 4, that would get us that. So either it's x squared over y, x squared times by y, or y over x squared. The measurement of a physical quantity may be subject to random errors and to systematic errors. Which statement is correct? A systematic error cannot be reduced by adjusting the apparatus. It can be. Systematic error results in a different reading each time the measurement is taken. That is the random error. Random errors are always caused by a person taking the measurement. No. By person taking the measurement, that would be systematic. By reduced by taking the average of several measurements. Yes, that is correct. Again, it could be reduced, not completely gone, completely eliminated. The Young modulus of a material of a wire is to be found. The Young modulus E is given by this equation shown. The wire is extended by a known force and the following measurements are made. Which measurement has the largest effect on the uncertainty in the value of the Young modulus? Now, the largest effect on the uncertainty of the value, that would be coming from the percentage uncertainties. So the largest effect on the calculated Young value of Young modulus would be shown in the high value of percentage uncertainty or fractional uncertainty of this. So this would come from force, this would come from length, this would come from d, and this would come from x. Now, we need to see which one of these would cause a highest spike in percentage values over here. So 0.002 divided by 2.043, I think you can already see that this is not going to cause quite a lot of effect. 0.02, so since this is times by 2, you have to remember that 2 times by 0.02 divided by 0.54. When you do this would cause a 7.4%. Actually, we should have written down what was the previous one. So force is coming once, so 0.01 divided by 19.62 times by 100. That would be 0.05%. And this one, x, 0.2 divided by 5.2 times by 100. This would be 3.8%. And just to do this again, divided by 2.043 times by 100. This is right. So this was 0.097. So clearly this has the most impact. Right. The density of a material of a rectangular block is determined by measuring the mass and linear dimensions of the block. The list shows the results obtained together with the uncertainties. The density is calculated to be this. What is the uncertainty in this result? Since density is mass per volume, we need to multiply these values for the volume. So the uncertainty in the density we need to find out first. 0.1 over 225 plus, because volume has length, width, and height included, so 0.015 plus 0.01 divided by 2 plus 0.01 a 1. And then for rho, we will, whatever value that we have calculated over here, we'll multiply this with rho, which is 2.5. So first, let's calculate this. So we have 0.1 divided by 25 plus 0.01 divided by 5 plus 0.01 divided by 2 plus 0.01 divided by 1. So this is the value. You can convert it into percentage if you'd like. So, sorry, no. This one would be 2.1%. Either way, it's either you write as 0.021 or 2.1%. Either way, it's fine. So this value, answer times by 2.5. We get 0.05, which is one significant figure, part C, option C. A solid bar has a square cross section. Its length is measured as this, width is measured as this. The values are used to calculate the volume of the bar. What is the percentage uncertainty in the calculated volume? So what we will do over here, since one of these is used as the length for the square cross section, so we need to figure that out. So percentage uncertainty of the volume will come from either this over 50 times by 2 plus 0.01 over 2, or it will come from 0.01 over 2 times by 2 plus 0.2 over 50. Let's see which one of them is correct and which one of them will make more sense. Divided by 50 plus 0.01 divided by 2. The percentage would become 1.3%. And for this one, 0.01 times by 2 is this, divided by 2 plus 0.2 divided by 50. This is 0.014, so 1.4%. So this is the correct one. And also they said its width is measured by that. So it's the width that is the square cross section. All right, so let's look at some paper 2 questions also. The list below shows some SI quantities. Underline the quantity that is not an SI based quantity. That is charge. Oh, sorry, we needed to underline that. Current, length, and time are base quantities. Charge is actually made from I and T, so derived quantity. A square solar panel with sides of length 1300 millimeter is shown. Light is incident normally on the solar panel. Calculate the intensity of the light. So intensity of the light we know to be power over area. This is from the waves topic. So 750 divided by, now 1300 millimeter, you have to convert it into meters. So divided by 1000, this would be 1.3. So this would be 1.3 square. 443. So 750 divided by 1.3 squared. This is coming out to be 443.787. So roughly about 440. The percentage uncertainty in the incident power is 3%. Uncertainty in the length of each side is 5 millimeters. Calculate the percentage uncertainty in the intensity of the light. Okay, so what we would need to do over here, we can do the percentage thing. So power 3%, that's already added. You can do it this way also, absolutely does not make a difference. For uncertainty in length, length is coming with a powered sign, so 2 times by 5 over 1.3, sorry, 5 millimeter, right. Now, remember one thing, that when you retain the same units, the percentage uncertainty doesn't change. So 5 over 1300 would give the same value as 5 divided by 1000, 0.0005 divided by 1.3. So, and then this is times by 100, which is, as you can see, the zeros will cancel out. Right. So percentage uncertainty in the intensity would be 3 plus 10 divided by 13. This is going to be 3.7 or 3.8%. Right. Okay. Moving on. Define density. We already know that this is mass per unit volume. Right. Figure 1.1 shows a cuboidal glass block. Student measures the mass m of the block and the side lengths x, y, and z. The measurements are shown in the table 1.1. Determine the density of the glass. Okay, so we need to do the same thing. I think we also did this in one of the previous questions also. So determine the density, mass per volume, x, y, z. So mass is 0.243 kilograms, and these ones need to be converted into meters. So all of them will need to be converted to meters. So since there are three values, we can divide by 10 raised to power minus 6, or sorry, multiply by 10 raised to power minus 6. So minus 2, minus 2, minus 2. So 5.41, 11.09, 1.62, and then 10 raised to power minus 2, minus 2, minus 2, compensated for that, so 10 raised to power minus 6. So this would become 0.243 divided by 5.41, 41, times by 11.09 times by 1.62 times by 10 raised to power minus 6. This would be 2500, and that's already in two significant figures, so that's okay with us. Calculate the percentage uncertainty in the density. All right, so for percentage uncertainty, we need to add the fractional uncertainties of all of these and then multiply by 100. So you have 0.001 divided by 0.243. And remember, for percentage of fractional uncertainty, you do not need to change the unit because fractional way would be the same. So 0.01 divided by 5.41 plus 0.01 divided by 11.09 plus 0.01 divided by 1.62. So 0.001 divided by 0.243 plus 0.01 divided by 5.41 plus 0.01 divided by 11.09 plus 0.01 divided by 1.62. This value 0.013, in percentage this would become 1.3%. So 1.3%. The true value of the density of the glass is different from the answer in B1 because of a systematic error in measurements. State one possible cause of systematic error. C, it could be due to zero error in the measurements of the lens or wrong calibration of the weighing mass in the measurement of the mass. So either way you can say that. So you could say that improper or incorrect calibration of, since we need that, so we could use the mass balance or vernier calipers. We don't actually know which measuring instrument they use, but since they use this one, this would be inappropriate for calipers. Even micrometer screw gauge would be fine. Whenever vernier calipers would actually make more sense. Right. Right. Okay. Right. Let's do one more. Similar question. Underline all the base quantities in the following list. So ampere is base quantity, base units, not quantities. So this is base quantity, but not the unit. Kelvin is a base unit. Toy car moves in a straight horizontal straight line. The displacement s of the car is given by the equation, where a is the acceleration, v is its final velocity. State two conditions that apply to the motion of the car for the above equation to be valid. So remember, this is actually coming from ut plus half. Oh no, sorry, no, sorry, my bad. This is actually coming from the 2as v squared minus u squared. So first off, these four equations that we use are based on the assumption that we have a uniform acceleration, and the only quantity missing in this is u, so that it assumes initial velocity was 0. Right, okay. An experiment is performed to determine the acceleration of the car in b. The following measurements are obtained. Wait, sorry. S is equal to v squared, right. Okay. Calculate the acceleration of the car. So basically all we have to do is to use the same equation, s is equal to v squared over 2a, to just cross multiply and find a. So v squared over 2s, v is 2.75 squared over 2 times by 3.89. So this would be 2.75 squared divided by 2 divided by 3.89. Oh, sorry, no. Divided by 2 divided by 3.89. So this would be 0.972, can be written as 97. Determine the percentage uncertainty to two significant figures in A. All right. So first we can find out fractional. Sorry, they're already given in percentage, so we don't actually have to do anything. So, oh, sorry, times by percent is equal to A was v squared, so 2 times by 0.8 percent plus 2 will not be counted, so this will only count 0.5%. So 1.6 plus 0.5, this is 2.1%. 2.1%. That's it. Use your answers in C1 and C2 to determine the absolute uncertainty in the value of A. So for the absolute uncertainty, we would multiply A with the percentage uncertainty that we figured out. So that would be 2.1% of, what was the value of acceleration? 0.97. So 2.1% times by 0.97. This is going to come out to be 0.02. And sorry, my mistake. This was not, I guess, May, June 23. This is, I think, February, March 23. Right, and I think that would be sufficient. Hopefully, we'll see each other in the next video. Bye bye. Take care.